We started section 4.3 last time, which is Riemann sums and definite integrals, and we're going to continue that section today. We talked about Riemann sums taking an interval and splitting it up into small pieces. We talked about the fact that the pieces don't have to be equal intervals, but we often let them be equal intervals because it's just easier to work with, and the result's the same either way. Our definite integral, we had this new notation, and it's boxed in right there, where it looked a lot like this notation we had from 4.1, but it had a number at the bottom and a number at the top, and the a and b are numbers. They're just represented right now as dummy variables. And it's equal to this summation that we encountered in 4.2. So this is sort of combining sections 4.1 and 4.2 together. We talked about the fact that if we have something that's continuous, it's automatically going to be integrable. But just because something's not continuous doesn't mean that it doesn't have an integral. Okay, so it doesn't work. It's not an if and only if statement. If it's continuous, it will be integrable, which means we can find this area. And we talked about the fact that when we're finding area, when we have area above the curve, your calculation will show that it's a positive area, and if we have area below the curve, your calculation will show that it's negative area. And when it adds those together, it gives you sort of this sort of net area feel. It doesn't actually give you the full amount of the area. So if you wanted the full amount of the area, you'd have to split it into intervals to actually find the components and then add them together physically. Okay, so we already did this example last time. Example number 1, we set up the definite integral. The picture is actually what we were given to begin with in the function f of x equals x squared. And then we wrote down that this integral would be the integral from 0 to 2 because we looked along the x-axis. The lower number was 2, the upper number was, the lower number was 0, the upper number was 2. Our curve was x squared, and then the dx and the script s at the beginning, they always go together. Okay, so it's telling us with respect to x. So let's take, that was the answer. Yeah, it just asked us to write the integral, to write the expression. That's it. That's all the problem asked for. Okay? So it's asking us to basically turn a graph into an algebra statement or a calculus statement, truly. All right, so what we're going to do next is we're going to sketch a region whose area is given by the definite integral. Okay, so we're going to sketch a picture on this one. And then we're going to use a geometric formula. Okay, so thinking geometry. So what are some geometric figures that you remember? Squares, circles, triangles, rectangles. So we're thinking about the formulas from geometry when we're doing this definition. And the key in doing that is because it says geometric here. Okay, so every time I do a question like this on a test, people try to use calculus to do the problem, even though it says geometry. Pay attention to the directions, okay? If they're asking you to use geometry, they really mean with a geometric formula for something like area equals, 1/2 base times height for a triangle, stuff like that, okay? All right, so this one says we want the integral from 0 to 3 of the equation 4. So we know that our x-axis is going to go from 0 out to 3. But what does the equation 4 look like? Okay, so be careful. I know what you mean by what you're saying, but you're not using quite the right terminology. All lines are straight, right? You mean horizontal. So let's do a horizontal line at 4. Good. And we want the area under this curve. Hang on, let me get some pins set up here. That'll work. So we want this area right here, right? So what is the shape? It's a rectangle, actually. Yeah, this is a rectangle. And how do you find the area of a rectangle?
Base times height.
Base times height. So what's the base?
3.
And the height?
4.
4. Or you might remember it as length times width. And either way you do it, you're going to get 3 times 4, which gives you 12. Okay, so what kind of shapes could you expect to see? Well, you definitely could see squares and rectangles. You could see triangles. You could also see trapezoids. Trapezoids are a very common figure. You could see a semicircle, right? The top half of a circle, that's a possibility. And after that, you're pretty well stopped with the geometric formula possibility, okay? In terms of an equation that they're going to give you and then a geometric formula that you would be using. So it's going to be one of those types of shapes. All right, so we have another one, same directions. This equation is 3x plus 4. So what is that an equation of?
Line.
It's a line, and we're going to go from 0 out to 2. This is a line with a y-intercept of what?
4.
Correct, 4. And it has a slope of 3, which means what?
Up 3.
Up 3 over 1. And we do that twice, yeah? So the shape looks something like this. And if we're finding the area from 0 to 2, we get this sort of a picture, right? So what is that shape? It is a trapezoid. If you don't like trapezoids or you just don't remember exactly what the formula was, because it's not one we use all the time, could you break this into a couple of pieces that you do know the formula for?
Yes.
What could you break it into, Fallon?
A triangle and rectangle.
Yeah, if you broke this apart right here, you could see the triangle and the rectangle. Do you guys see that? So you can either do triangle and rectangle or you can do trapezoid. So let's look at both possibilities just so you can see them. We'll do the trapezoid first. So if I'm doing a trapezoid, the formula for a trapezoid, does anybody remember it for area?
Like 1/2
Mm-hmm.
base 1 plus base 2 times height.
Very good remembering, yeah.
Oh, man.
Okay, now the thing you have to remember about the base 1 and base 2 is it's the parallel sides.
Yes.
Okay, so it's not just top and bottom. We kind of think about that a lot because in geometry we usually see trapezoids drawn that way, but it's really the parallel sides. So what is your base 1 and your base 2 in this picture?
Like, let's see, 4.
One of them's 4 right here on this side, right? And what's the other one? 10?
Yes.
That sounds right. And this one's 10. So 10 plus 4, or 4 plus 10, and then what's my height? 2. So the height for this would be this length right here.
So they just cancel 1/2 and 2.
Yeah, on this one, the 2 and the 1/2 will in fact cancel. So we end up with an area of 14, right? Okay, then let's think about it if we did a triangle plus a rectangle. Because we could do it that way too, right?
Yes.
Okay, so if we did a triangle plus a rectangle, let's do the triangle first. So the triangle's on top. What's the area of a triangle? 1/2 base times height. And because this is a right triangle, it doesn't even matter which one we identify as our base and our height, right? It's sort of interchangeable. So we have, because this is a right angle here. So what would we get for this one? What's the base, what's the height? Either way.
1, 4, 2.
One of them is 2. What's the other one? 6, right? So this piece right here is 6, and this piece is 2. Obviously, it's not drawn to scale. Agreed? Yep, and then we would need our rectangle. So what's the area of the rectangle?
4.
Length times width, which is 4 times 2. So on the first one I got 6, on the second one I get 8, and if I add them together I get the 14. So 2 different ways to think about this particular shape, trapezoid or triangle and rectangle. Okay, a couple of special definite integrals, and I alluded to the possibility of doing this last time, but we hadn't gotten there yet. So f is defined at x equal a, then if you have the integral from a to a of f of x dx, it's 0. Why would that make sense?
Because you have there's no dx length.
There's no width, right? If you're starting at a and you're going to a, there is no area because there is no space under the curve.
Yes.
Okay. Yeah, what's that? Yeah, it would be just that point. But because we're calculating area, you can't calculate the area of a point. It's 0. Or you can calculate it at 0, I guess you could say. All right, on number 2, what do you notice on number 2 that looks a little different than what ones we've done so far?
The A and B are switched.
Yeah, this one actually shows what happens if you were to switch the limits of integration. So if your limits of integration switch places, and there are times when that's a helpful thing to do. I'll show you examples, I think, later on. But if you change the limits of integration, it keeps the area the same. It just changes whether it's positive or negative. Okay? So it's just switch the limits of integration, you change the sign of your integral. All right, I don't know why that's there. Let me clean that off. Okay. Additive interval property. If f is integrable on 3 closed intervals determined by a, b, and c, then the integral from a to b of f of x dx is the integral from a to c of f of x dx plus the integral from c to b. This is the picture that this is describing. You start at a, you end at b. That's what the interval would be on the left. You've got some kind of curve, you drew the area between the curve and the axis. And if C is a location then that is lying between them, Then it would be the same thing if you broke it up to go from A to C, and you looked at the piece from B to C, and then you added them together. And that's kind of what we did with that picture about our trapezoid, right? Not exactly, because I drew it so that the breaking apart was actually above the axis. It didn't come all the way down. But it has the same feel to it. I could be able to break apart the area and add the area together in pieces. And that's all this is saying. Does that make sense? And that's the reason that it doesn't matter if the integral actually is continuous, not the integral, but the function is continuous on the whole interval. If it stopped its continuity at point C, it had a hole in the graph, say, no problem. We'll just stop our integral and go from A to C, and then we'll pick it up and go from C to B. That's why we're allowed to do that, is because we can break it up into these pieces. All right. Theorem 4.7's talking about properties for definite integrals. F and g are integrable. K is a constant. Kf and f plus and minus g are integrable. So we get the following. So if we have a constant times our function f of x, we can pull the k for the constant out in front, and we can just find the integral. Feels a lot like derivatives, right? We can do that for derivatives. You take just the derivative of the variable piece and you multiply it by the constant. So it's a constant multiplier rule. The second one, same kind of an idea. I can break apart addition and subtraction and do them individually. So I find the integral of the first piece and I add or subtract it to the integral of the second piece.
Okay.
So these feel very much like two of our properties for derivatives. The sum and difference rule and the constant multiplier rule. And we're going to use these facts on the next two examples to find areas that we don't know using areas that we do. Okay, did everybody get all those written down? Yeah, we're good? Oh, not quite? Okay. All right. So to start with, read the directions and use them. You guys think that I just am weird when I say that stuff, but you have no idea how many times students just fail to read directions. So, oh, that was you, was it? Okay. All right, so this one tells you to use the following values to do this. Now, once we get into section 4.4, we'll be doing this in a different way. So pay attention to the directions on the problem you're working on. Maybe it doesn't so much matter on the web assign, you're going to get the same answer either way. Okay, fine. But when you get to the test and you're actually showing your work or a quiz or a written homework you're turning in or something like that, that's when it becomes more important, right? Because then your work is graded as well as the answer you're getting. All right, so they actually give you three integrals. They tell you all of them are going from 2 to 4. One of them is the integral of x cubed, one of them is the integral of x, and one of them is the integral of a blank dx. Okay, there's nothing in it. What do you think that dx means like that by itself? This showed up on some of your quizzes, didn't it? But what do you think it is?
0.
There's 1 there. It's just like x. What does x mean? Well, it means 1x, right? There's a 1 there. So it's like essentially having a 1. All right, so we don't need that fact for the moment, but we're going to take what we have right here and we're going to break it up. Because it's addition and subtraction, I can break up into 3 integrals, right? So that's what I'm going to do. I've got my integral from 2 to 4 of x cubed dx minus the integral of 3x, I'm sorry, from 2 to 4 dx, and then plus the integral of 8 from 2 to 4 dx. Now the first one looks exactly like this, right? It looks exactly like one of the pieces I was given. The other two don't yet. I need to change them one more time in order for them to actually be able to be substituted in properly. So the 2 to 4 is cool. I don't need to do anything. I mean, the first one, the x cubed, is cool. No problems. But what could I do for the second one so that it looks like one of the integrals I actually was given? Yeah, we're going to pull that 3 out in front. So 3 in front, and then it's the integral from 2 to 4 of x dx. What about this last one?
Pull out the 8.
We're going to pull out the 8. Same thing. 2 to 4 dx. Now, the reason that that's valuable is because each of these 3 integrals now is exactly an integral I was given the value for. So now, and only now, and never before now, can you actually substitute those three values in. The first value was 60, and then it'd be minus 3 times. The second value is 6, and then be plus 8 times. The third value is 2. So, what is the integral, or what is the sum of the values here then? What is 60 minus 18 plus 16? 58. Okay,
It's not gonna be that easy on the website, is it?
I don't know. We'll see. You guys complain so much more about WebAssign than my last class did,
Website is
just so you know.
hard 'cause it's so confusing.
I mean, I'm not saying it's not valid complaints. I'm just observing. Okay. Taking a look at number 5, last example in this section. Tell me something you notice.
It's got an X, but it has a minus.
Oh, okay, so
4 to 2.
it says 4 to 2. The limits of integration are flipped, right? But we know how to change that, correct?
It's just a negative.
All right. So our very first step is to rewrite this with the limits of integration sort of rewritten or switched or in order, however you like to think about it. So now I've got a negative in front and I've got the integral from 2 to 4. Now what?
Rewrite, break it up.
Now we're going to break it up. Now that negative in front will apply to both pieces, okay? So you're going to have an integral from 2 to 4 of x dx, and then you're going to have a negative and another negative, so this will, well, let me just write it this way for now.
Okay.
Just so everybody sees it. Do you see the negative in the middle and then the negative on the 7? Those will cancel, right? Be plus. And then I need to do one more step before I'm able to actually use the pieces of information that I was given. I need to pull out a 7.
Okay.
So this will be plus 7 integral 2 to 4 dx. Okay, so I've got a negative here. What's the integral from 2 to 4 of x dx? So it'll be a negative times the 6, right? And then I have plus the 7 times, and what's the integral from 2 to 4 of dx? That was 2. So I have negative 6 plus 14, which gives me 8.